Hey guys, what a week, huh? So there's a little bit of snow, a little bit of whatever. Doesn't look like much is alive out there, but you know what? Everything's alive out there. It's going to come back here soon, the next few weeks. We're going to work on creating a model, and I've already tried to do this with paper, and like the old-fashioned way of creating a model of something, and just decided that it wasn't worth it. So we're going to do it in Excel because Excel is a whole lot more fun to use anyway. So if you pull up Schoology and you're looking at the assignment I've given you, specifically the Sixth Extinction Shenandoah Valley style, a little play on at the time of the Gangman style. Anyway, so um, we're going to look at the equation S equals little c times big A to the little z, and this relationship was formulated by E.O. Wilson. It was originally observed by others, but E.O. Wilson and oh gosh, Wilson and they did two authors there. Not just Wilson, was another guy. Anyway, when they put this together, when they quantified it, it's essentially become a law. So it's a species area relationship, sometimes not really referred to as a law, but typically when we quantify these relationships we see in nature in a mathematical manner, that's typically what a scientific law is. And so this is like the only law that exists in ecology. And basically, it was designed for islands. And so, if you go out in the middle of the ocean and you find an island with a particular size, and you're able to characterize its climate or whatever, ideally that's done with the c variable because that gives you a foundation, a place to start with. That's your y-intercept of the equation in log space. Because obviously, when you look at it the way it's written in Schoology, that does not look like a linear equation, does it? If you look at the logarithmic version of it, it is a linear equation, and of course you're gonna produce lines. Otherwise, of course, it's a power equation. So power function. So anyway. The bottom line is z is usually used to characterize a particular group of organisms or whatever. So those values tend to be exist between a narrow range of roughly 1 to 3. You have to sort of tease out where that is. And then, of course, A is area. So the surface area, the bottom line is that the area of a location is directly related to the number of species that live there. That's the bottom line. The other two things, the C and the Z, are really indicative of the locality or the particular organisms that you're looking at or whatever. And so they tend to vary. And the way you figure them out is by actually going out in the field and doing surveys. Take a plot of land of 10 acres or whatever and identify every species you can find. And that gives you an idea of, you got the area, then you can get the S value, and then you can start to characterize the C and Z values more easily. So what we're going to do is we're going to create a model here where you can, for the Shenandoah Valley, quantify these things. And so the first thing you're going to want to have in here, of course, is if you look through before we get to that, there's a couple of studies I've given you. So your job is to create a numerical model. There's 2 attached articles that'll help. I didn't find data on our local area, but I did find a U.S. Forest Service publication that looked at Western North Carolina, which is not too far off from our area. And then that area had 20 by 50 meter plots that were examined, and so the numbers you see for number of species are based on a 20 by 50 meter plot, which is 1,000 square meters. Okay. And then the table 1 of that lists the results of the survey of these forests. So if I have an area, let's just say here, area 1,000. Okay. Actually, we'll put that down here, 1,000. And area is going to be in square meters, right? So if I have an area, 1,000 square meters, I'm going to get my species value from that location. So I look at table 1 in there. I'm going to pull it up now. You should be able to see it. If I go down and look at table 1, that's table 2. Right. So here's my problem. Of course, here's my plots. Here's the plot number anyway, and then the number of species they found. The trouble is I've got these that have high taxonomic resolution, which is really, really good. And what they've done here is they've gone and looked at whether or not they could actually find the particular location, but you don't know where these things are, right? So what you need to do is just pick one of these that you think is indicative of the area, and it's gonna be hard for you to figure that out as well. So don't spend a ton of time on it, but you can start to look at this a little bit. But let's just say let's just pick one for the sake of discussion right now, and let's look at the Highlands, North Carolina area. All right, so that's plot number 92 with 875 species. All right, so in that plot we had 875 species. The trouble is now, of course, I don't have a C value or a Z value yet, right? So I can't actually do much with this. Like if I knew the C value, now I could figure out the Z value and so forth. All right, well, what do I need to do here? So so then you need that's where you get the A value, right? And so then you need to go to the next publication. So our goal should be to calculate Z values. They're the most typical for a location. So which C values? So look at table 2 from Gerstner. I'm going to pull that up as well here for you. So table 2, now of course this article was this article is actually looking at a global scale here, so it's relevant. And if we scroll down here, this is table 2 here. That's where you're going to pull your C values, but excuse me. But you can see they're actually looking at everywhere on the globe, right? So that actually works out quite nicely. Anyway, if you think about if we look at the global model versus the biome model versus the land cover model, what kind of land cover do we that's indigenous to this land have? It's not tropical and subtropical. It's temperate, right? So we have several options to choose from. We've got temperate grasslands, savanna shrublands, but we're more like temperate broadleaf mixed forests. We do have some temperate coniferous forests in the highland areas, but we're mostly broadleaf and mixed forests. So um, if we look at that, our C values here, which is the y-intercept of this equation, is one C value you could use is 2.468. There's actually a Z value here you could use also, for that matter, that 0.161. So if I 2.468, right, and then I could, here I ask you to back calculate the Z value based on what you have here, right? And so I haven't done this yet, but if I were to go ahead and do that, what would I need to do, right? I would need to rearrange the equation to solve for Z. And so, of course, I'd have to do some machinations to do that. And I think you guys can do that basic algebra without me belaboring it right here in front of you. So you can back calculate Z. You could, of course, also use their predicted Z value of 0.161. And so maybe it's Z Gerstner equals, what was that, 1.161. So 0.161, right? So you can see what does your Z value turn out to be, right? As you calculate it, first thing you need to put is an equal in there, right? And then rearrange the equation, and I would probably do that on a piece of paper somewhere, and then solve for Z. Okay. So anyway, now the next thing I ask you to do though is to figure out what from there to create 10 data points for a model where you can then figure out what species richness for I say your county. It could be your county. That's the best way to do it, because you can look that up really easily. So if I look up the area of Shenandoah County, VA, actually Google pulls it right up, 512 square miles. If I then convert 512 square miles to square meters, I get a crazy number, 1.326 times 10 to the 9th, right? So the area of Shenandoah County, right, is if it's at 100% of the, let's just do this. Just do this. So did I just do that? There we go. All right, I'm making this up as I go, by the way, guys. So I'm just showing you one way you could do this. There's other ways you could do that. So I'm gonna do that. I'm gonna go ahead and put in a C value, a Z value, and then species richness. Which is what we really want. We want to calculate this, right? So what we want to do then is we're going to go ahead and say 100% here, and we need 10 data points. Let's just go with 90, 80, and so forth. Now, if I did this right, I highlight these. Yep, it's going to do it. Boom. Yep, cool. I can start here with that crazy area, which is 1.326, and in Excel, the capital E is a -9. It should recognize that, of course, and it does. If you look in the formula bar, it's already converted that. But that's not really what I want here. What I want to do here is do this. Actually, what I'm going to do is with percentages, I'm going to do this. I'm going to say this is 1. I'm going to say this is 0.9. Actually, no, this is going to be 1. Yeah, 0.9. This is 0.8. And I'll show you why I'm doing that here in a moment, because that's actually what a percentage is, right? So we're going to convert that. And over here, I'm going to say, instead of doing that, I'm going to say equals this times 1.326 e to the -9th. And then, of course, it should be the same exact thing. Now, if I drag this down, it should automatically calculate my areas for me, right? And these areas are going to get smaller and smaller. So that this was the biggest one. Well, that's positive 9th. Okay, 1.326. This is what happens when you're doing this on the fly, and you're not thinking. So let's try that again. Okay, so these areas are getting smaller and smaller. As you can see in the over there, they're still going to be put. That's still automatically putting them in scientific notation, which you could change if you wanted to. You could just go up to the number here, and just put it as a number, and there you go. And you don't need the decimals, so you can adjust the decimals. Oops, wrong way. Doing that. Now I've got my C value, right, which we figured out from that publication here, and then so what I need to do then is put. This is where I'm going to go ahead and put in 2 point. Actually, I don't even need to do that. I can actually take the C value out because I don't actually need to grab that. And the Z value, I can keep that also. I can just pull the C value from up here and the Z value from here. Or actually, you're going to pull it from here once you figure it out. But what I'm going to do here is I'm just going to put S over here and get rid of that. Okay, so this is what I'm going to do. I'm going to make an equation here. All right. So I want S to equal C times the quantity of this, all right, to the Z power. Now, if I do that, there's a problem. All right, it's probably going to be, yeah, this is probably what's going to be here. And actually, I'm going to put the F2 in there, and I'm going to get rid of this over here, and that should fix. No, that should have fixed that. All right. Sometimes I've got to figure out what I'm doing wrong as well. If I put in parentheses here, still doesn't like it. Now, B5 to the F2. All right, let's do this. I don't think I actually need this one over here. Still getting a value issue here. Okay, so here I'm back. Rather than trying to do it all at once, rather than spending time on the video here working on that, I'll work it on my own. I'm sure you guys will figure it out before I do, before I'm able to talk to you about it. Anyway, it's a simple little syntax thing, I'm sure. What I've done here is I've done the A to the Z power, and then calculated species separately. No big deal. So to do that though, I just wanted to do B5 to F2, So B5, of course, is this value. F2 is up here, is from Gerstner, right? And I really think this number is going to be too small. And I'll tell you why in a moment, but let's look at it. All right, this is not important here, so we get rid of that. All right, so if I look at what I did here, I did B5 to F2, but I want F2 to be the same for all of these values. So in order to do that, I put a dollar sign in front of the F and a dollar sign in front of the 2. And once you do that, of course, you hit enter, and then you drag it on down, and you get your values. Well, this one's a lot easier because all you have to do is multiply C times this value now. And again, you want C2 to stay the same the whole time. So again, you put dollar signs in front of C and 2. You got to put some bling in front of it for that to happen. And once you do that, of course, you end up with these values. Now, let's think about what we're looking at here. So this is my little model here, and my little model is just this is just a really quick model, and it's not necessarily all that accurate, right? I do have data points. I can in fact take these data points and graph them. Now, I don't really want to graph this last one because it's really not all that useful to me. But if I were to scatter plot these bad boys, that's the insert menu I want. Right there's my species area graph, and it goes all the way down to 0, and actually it would go all the way down to 0 here. Now, if I wanted to take this and put it into a format that would make more sense, I will double click on this, and I can turn it into a logarithmic scale, and I can do the same thing here and turn it into a logarithmic scale, and then it looks like that, right? I can then fit a trend line to this, and if I fit a linear trend line, it doesn't quite know what to do with it, right? If I fit a exponential trend line, it's not even showing up on there, is it? Oh, it's there. It's there. I want to extend that out a bit. I'm going to go back. Let's see, we'll forwarded. Take this period. Actually, let's go ahead and forward it out 1,000 periods. Trend line should be getting bigger. I'm trying to forecast it. It's just hard to see. I can, of course, adjust these things. Anyway, you can play with the thing, but there's the line anyway, and the species area relationship. Play with the scale, get it to work. That's fine. Get a trend line on there. That's the kind of stuff I'm looking for. What I really want you to do is have this stuff where you can analyze it. Now, let's think about what we got here, though. Okay, so this means that in the entirety of Shenandoah County were covered in forest, temperate broadleaf forest, okay, there would be 72.62 species. Now, I don't know about you guys, but it seems a little low to me. I think I could go out here in the back 40 here at Triplet and find 72 different species in the lawn. I mean, I'm quite serious. So I don't know what you're going to calculate for Z values yet. I mean, it's just rearranging the equation, guys. I can go do it right now, but I'm not going to. I'm going to let you do that. But let's just play with the Z value. Let's say these don't generally go much higher than a little over 2. But let's go ahead and put this at point. Let's see how sensitive this is. A little sensitivity analysis. Let's put this at 0.5. Okay, now watch what happens to the numbers here in this column when I hit enter. Boom! Look at that, right? Now, this is why it's a model. What I put together here is far from perfect, okay? And there's mistakes I've made. I can go back and tweak it. This is not meant to be at a time where there's, it's like any model. Models are always wrong, but some are useful. Well, this might just be a useful model. Let's change this value to 1. Whoa! Look at that. Whew. Those numbers get really big, right? Some big numbers. Suddenly, with a Z value of 1, I'm looking at, millions of species. If I go down to a Z value of 0.05, then I'm looking at a pretty species poor area. Now, I can, of course, convert this back to a regular old arithmetic scale and watch how things. I'm going to go ahead and get rid of that trend line. I don't like that. There's two trend lines there. And so more trend line options. By the way, if you hit more trend line options, you get a bunch of other options, and of course the power function fits this nicely. And so there's your trend line. But if you can watch things change. Now this is blown up really nicely. If I put this back at 1, you can see what happens to that. I mean, it basically straightened it out. It's pretty phenomenal. What happens if I add the bottom one on there? And so if I select my data here and I edit my series, and I go down here specifically, instead of ending at B14, I end at B15. Do the same thing here. Yeah. So what happens is it's just warning me that the trend lines can't be calculated from data that contains negative or 0 values. I hit OK. It'll extend it, right? And it extends it down to 0. But this is a problem, though, isn't it? Because my y-intercept is supposed to be 2.468. So this is one of the reasons why I didn't include this particular value. Models are always wrong, but some are useful. And I know that my y-intercept is 2.468 in this model. But if I, when I calculated things, my last, of course, if there's no area, I mean, obviously we're looking at a situation of extinction over here. And if this is the case, right, you wouldn't expect there to be any species left if all of that forest is gone necessarily. But that's not the case, really. In reality, based on the species area model, species area relationship, we should have 2.468 species still there. And that's what that number is essentially getting at. It's like your base number of species that exists if that environment is, completely gone or whatever the case is. If there's no island left, which is a really hard thing to conceive. So this is one of these situations. It's like traveling into the center of a black hole, right? You got all these great equations for gravity and everything else, and even calculating the Schwarzschild radius of a black hole and so forth. But when you get in there, it all breaks down. And these laws, they have their limitations, and you're looking at one of them here with this one. So anyway, I'm going to stop it there, but you guys got an idea of how I put it together. You can do it how you want to. If you've already submitted it, I know there's 2 people who have, and then you go watch this video, you may decide to change a few things and resubmit it. That's fine. But try to have some fun with it, okay? This is what we would have done in class this week. All right. Hey, take care. The snow will melt and the rocks will reappear. The interesting stuff is still there. It's just buried under that icy stuff. So just rest assured, it'll all go away, and we'll be able to see the cool stuff again. Until Friday, we'll talk to you later. Bye-bye.